Hello everyone, can you hear me? Yes. So in the last section, we were talking about handling duplicates, missing values, etc. Duplicate records, removing the duplicates, and sorting. Yeah, there were so many items, data handling things that we were talking about. Now today we'll start with data sets merging and joining. What is joining the data sets? Not every time we might find the whole data in one particular table, because the real-time databases, they might have multiple tables. All the customer information will be in one table, sales information will be in one table, store information will be in one table, order information will be in one table. But to get the exact data that we are looking for, we need to either merge them or join them, either left join, right join. So these are called SQL joins. So joins are also possible in R. So basically, if we have dataset 1, dataset 2, we just have to use the function merge that will join the datasets, dataset 1 and dataset 2. We need to mention the primary key, so that will uh, based on the primary key, the datasets will be merged, and the type of merge also need to be mentioned here. So if you are not really clear about what is joining, what is merging yet, I mean, this is the first time if you are hearing this, maybe in the SQL class that we are going to have, it will be very much clarified. The concept is pretty much simple. You just need to understand the syntax here, and if you don't have any idea on joins, you can spend a specific amount of time while we are dealing the SQL class. There will be a detailed discussion on merging, and there will be on joins, and there will be many examples on joins. So the way we do the inner join is we put dataset 1, dataset 2, then the primary key, all equal to false. So all equal to false will make it as inner join. If you say all equal to true, that will make it as either outer join, or it's also known as union. Left outer join, the left hand side data we want it completely, and whatever is matching on the right hand side data, matching from the right hand side data, if we want to just take all the left hand side data and then match it with the right hand side data, and whatever is required from the left hand side data, that will be printed. That is called left outer join. For that we need to write all dot x equal to true. Right outer join, the same way, the opposite of the above example, we have two dataset 1, dataset 2. We have to give the primary key and all dot y equal to true. Y, I mean datasets x and y is the second dataset, all dot y equal to true. That will make it right outer join. That's how we can mention it to R. Okay, I'll show some examples here. I am getting two datasets here, that is orders data. So there is a data called orders, dim of orders. How many observations are there? There are 1300 observations. There is a data set called slots. So I have downloaded orders data, I have downloaded slots data. Now I'll see the order of how many observations are there in orders, how many observations are there in slots. Now here is the intersection. If I want to see what are the common observations in both orders and slots, so there is this dataset order, there is this dataset slots. What are the common observations on based on unique ID? Is there any unique ID? Based on that unique ID, are there any common observations? That is also known as intersection. So the way we do it is we have to use the function merge. We have to give dataset 1, we have to give dataset 2, and then all equal to false. That will make sure it is going to be an inner join. So I'm creating order slot common, that is intersection. And what is the dimension of the intersection? There are 8 observations that are common, and overall 25 variables are coming up. So we can see that data actually. So this is the data that is common. I mean, these unique IDs are common in both of them. So there are just 8 of them. In fact, if you see the overall observations in orders, there are 1369 observations in order, there are 1764 observations in slots, only common observations are 8 based on unique ID. What is left outer join? Let us suppose if I want all the data from orders, I want orders data, left side data, I want it completely. Whatever is matching from the right hand side data, I just want to attach those data points. I just want to attach that information, because orders has how many variables? 9 variables. Slot has 17 variables. So my final data set will have around 26 variables, but it will have only 1316, and all the data from orders. The left data will be completely populated, and anything that is matching from the right hand side data, that will be uh, populated in that final file. So order, slot, all match. So what we are trying to do here is we are trying to get the left outer join. So this is the left outer join. As we expected, the number of observations in order and number of observations in the left outer join will be same, because we are just, and the number of variables in order is 9, number of variables in slots is 17. So the new one has 26, but unique ID is anyway repeating in both of them. That's why 26 minus 1, 25 will be there. The way we do right outer join is exactly the same way. We take the data orders data, we take the slots data, then we take it by unique ID, all dot y equal to true. So that is like, we want to take all the observations from slots, whatever is matching from orders will be attached. So the final data set will have exactly same number of rows as slots data. So here is the right outer join. Final data set has exactly same amount of rows as slots data. Now what is union? All the unique values, all the values that are there will be appearing. Orders plus slots minus the common ones. So we are just want we just want to do the union of all the data that is available for us. So the union has 3125 observations, 25 variables. Just wanted to check, Venkatesh and Bhargavi, do you have any idea on SQL joins beforehand, or is this the first time you're hearing? Okay, so you have no idea on SQL. So in that case, we will skip this exercise. Okay, maybe next time once we finish SQL, you can come back, and then only you will be able to understand what exactly is this. Okay, I mean, there is a specific explanation that we can give, okay, just for this understanding this joins. Okay, so I'll skip this exercise for now. Anyway, I'll send the code. If you learn it by yourself, those who know it, they can just practice it. It's not a big thing. The data set in the lab will be telecom bill data and complaints data. So you can try out on these data sets. Exporting the data out of R. So let us suppose we have created a data set inside R. We finalize something and we want to take it out of R. So for reading the data, we use read.csv. Again, for reading the data, we are using read.csv. For exporting the data, how do we do it? Let's say I'm creating a data set here. I'm getting the duplicates, and then I'm getting the unique values. Same way I'm getting the complaints duplicates, unique values. Okay, this is joins, so I'll skip that. Yeah, exporting the data out of R. Let's say I have this bill data, or air passengers data. So this is the data set that we have, or cars data. If we want to export the data outside R, we just need to use the function write.csv. WRID write.csv. Put the dataset name, that is whatever it is called inside R. Write the exact file name and the path that where you want to export it to. it will be exported there. Either write.csv for CSV file format if you want the data set to be exported as a CSV file, write.csv. If you want the data set to be exported as text file, write.txt. So you need to mention the right uh, path, then it will be exported in there. Here if you put a dot, it will be exported to the parent directory where R is installed in, maybe, I mean, where the default path of R is. Most of the times it is to my documents. Okay, so write.csv is the command that we have to use. So I'll try to export this bill data same way. So first what I'll do is I'll try to export the bill data into a CSV file. I have the bill data 9642 observation, 7 variables are there. I'll try to export the bill data into that path. Exported. So let me see. My R path is connected to this one. Uh, where exactly is it? Telecom data analysis, bill data common.csv. Nope. I don't want to export it there. I just want to say export one. Export one. Write.csv, and then I'll say export one.csv. So I'm just writing this bill data inside this, or else if you want to write it in a specific directory, let's say I want to write it in desktop. Okay, I just have to copy the let's say copy the path, um, desktop temp. So that is where I want to export it to. As we know, if it is Windows, it has to be this way. So I'm exporting this bill data into export1.csv, where it will be on desktop. There is a temp folder and it will be exported as export1.csv. Export done. So you can see on desktop on this temp folder export1.csv is there. This is the bill data that we just exported from there. So let me delete this once again and show it to you once more. So write.csv, bill data is what I want to export. I want to export it as export1.csv. So export1.csv. What if I want to export it as a text file? Then I have to use the function write.table export to.txt file. If I want to export it as txt file, this is how export to.txt file, and you can see that it's a txt file exported as a txt file. That's how you export the data sets. Why we need data exporting? Why not directly work with R? Maybe right at the end of the analysis, you have created the file, you have created the analysis results that you wanted to take out. Maybe at that point you want to take it out as a CSV or TXT file. Okay, so try to export any one of the files as CSV and TXT. Just try it quickly. Bill data itself, maybe get the bill data inside R. Try to export it quickly. Just try it out. Once you are done, let me know. Just import bill data, telecom data analysis bill data, and try to export it, or take a subset of that bill data or do something, or directly export it. This is just to make sure our export, we're practicing export out of R. Once you're done with it, please let me know. Okay. So we are done with the data handling part of R. To be honest with you, there is nothing really tough in data handling portion of R. Okay, we saw some basic commands, and it's all about just knowing, what command works when. As you keep on working on these data sets, then you will get to know, or you will be very familiar with data handling tasks and all that. Okay. And let me tell you, joining the data sets is a very important concept. So we will definitely spend a lot of time on it when we are doing the SQL topic. And there are many topics within data handling, but some of the topics that we have discussed here, that what is sorting, how do we sort, how do we remove duplicates, how do we do basic data exploration, all those things are very important concepts in our future projects point of view. Okay, so that is it with data handling. Now, in the next topic, we are going to learn basics of statistics. I would like to pause here, and I would like to take questions if there are any. Are there any questions? Now we are going to discuss about basic statistics, graphs and reports. Before you even start data analysis, statistical concepts are the basic statistical concepts. You should have clear grip on them, then only you can move on to data analytics later on. So in this section we are going to learn some of the concepts like taking samples out of the data, what are some central tendencies, what is variance, what are percentiles, quartiles, what is box plot, some of the other graphs we will try to discuss about them. So first we'll start with sampling. What is sampling? Instead of taking the whole data set as it is, we will try to take a subset of it or a random subset of it. Let us suppose there is a huge data set. Here I'll take an example of retail data. Let me import retail data. Now this retail data looks like it is huge. It has n, how many observations are there? Almost 541,000 observations are there. So there are 541,000. So basically it's almost 500,000 observations are there. So if this data set is that long, if I want to, I mean, while doing the analysis, if we don't want to take that, or if we want to work with a sample of it, then we can use a function called sample. So the way that we do it is we write the data set name, that is retail data. So what am I trying to do here? We are writing the data set name, and then we are using a function called sample. So here is the syntax. So the dataset name is retail data. Now I'm using the sample function on the rows. So how many rows, how many ever rows are there? Let's say in retail data, around 500,000 rows are there, right? So from 1 to 500,000, from 1 to n row, what does this n row tell us? So n row is nothing but number of rows inside that retail data. So there are 541,909 rows inside that data. Then I want to take a sample out of it. What must be my sample size? It is 10,000. I just want to take 10,000 samples out of them, randomly taken. This comma everything means all the observations, I mean all the columns. Only 10,000 randomly selected observations. The sample set will have 10,000 rows and all the columns. The retail data set has the retail data set has 8 columns, 541,000 rows, whereas the sample set that is created like this, data set name, sample from 1 to number of rows, and then the sample size. This one will have 10,000 10,000 rows, and columns will be exactly same as overall columns. So I have taken a sample out of retail data. So this retail data is the data set name. Then I'm doing the sampling. How am I doing the sampling? Between, so you can also write the sample like this. So instead of saying 1 to all the rows, you can say I'll consider first 1 to 500,000 only. I'll consider from the data set 1 to 500,000. I'll take 10,000 randomly chosen values from the retail data. You can do that way also, or technically correct way is whatever is the size of the retail data, you just put it there, 1 2, and or if you are really confused here, you can simply remove it. We know how many observations are there in retail data. So from this to this range, we want to get 10,000 observations as a sample. So sample set, dimension of sample set 10,008 rows. Is that clear? Okay, so let's do an example. There is one census income data. Okay, that data set might be large. What we want to do is we want to randomly select a sample of 5,000 records. Try it out. Census income data. Try it out on the census income data quickly. Get the census income data. How many rows, how many columns are there? 32,000 rows are there. 15 columns are there. Out of that, you want to take only 5,000 sample size. Try it out. Once you're done, let me know. The way we are going to do it is I'll write the dataset name within brackets, the function that is sample. What is the range that I want to use? From first row to the last row, that is 32,561 rows are there. What is the sample size that I want to do? Take 5,000. Am I interested in all the columns? Then I leave it blank. Let me save everything in a new file, sample underscore income, sample details form. Instead of writing 32,561, I can write it programmatically correct way. So this way also can be written. Sample income. What is the dimension of sample income? This is. Are you done with it, everyone? Shall we move on? Okay. So the basic descriptive statistics. What are basic descriptive statistics? As soon as we get the data, we can find out some basic descriptive statistics. They give us a overall idea on the variables and their distributions. Okay, we can get a very quick idea on the overall data set, how it is, and what are the variables. Okay, what some of the indices we can observe and find out whether the data is correct or wrong, or we can basically get the overall picture of the data, maybe basically creating a simple report out of the data set. These are called basic descriptive statistics. So they help us in analyzing the data using few small matrices and indices. So quickly we can get an idea on the data set. Okay, so there are two types of basic descriptive statistics. They are called central tendencies and dispersion. Central tendencies are mean and median. Mode is also there. Dispersion, measures of dispersion are range, variance, standard deviation. We will discuss about each one of them. So mean, median, you might have already heard. Sometimes just calculating the mean, calculating the average gives us a very good sense of what is happening with the data. Mean is nothing but the arithmetic mean. It is nothing but the sum of values by count of values. Basically gives us a very quick idea on the average of a variable. Where is the middle point? Mean, everyone knows it, right? Like we don't need to discuss it more. Now what is median? Median is not known by most of us. Like what exactly is median? Mean is the one of the good measure of average or the middle point, but mean is not a good measure when there are outliers in the data. What do you mean by an outlier? An outlier is one value that if some of the values in the data are particularly different, very vastly different from rest of the values, or a small set of values are very different from rest of the whole data, then they are called outliers. When there are outliers in the data, then mean is not a good measure. Okay, if you look at this data 1.5, 1.7 and all that 1.1, look at this data, tell me what can be the average. Just guess it quickly. What can be the average of that data set? Yeah, what can be the average of this whole data that you are looking at from starting to the ending? Yeah, around 1.4 or something like that, right? Around 1. So at least you can expect the average to be less than 2. But the problem is the average for of that whole data set is exactly 2. 90% of the 90% of the values are less than 2, but still the average is 2. The whole data set that we are seeing here, 1.5, 1.7, 1.9, 0.8, if you see all the points, they almost look less than 2. But if you actually take them into calculator and start calculating the average, you will get the mean as 2. The reason for that is there is an unusual value or the outlier value in that above vector, that is 9. You see this here, there is a point 9. Because of that one value, the whole mean itself is thrown out as 2. Now what is the problem with it? We ourselves are admitting that 90% of the values are less than 2, but we ourselves have to say the average or the mean is 2. Now that is a problem. So that is the reason why what we want to do is we want to calculate a better central tendency or a better average value, okay, that or adjusted average value or the true middle value. Okay, what is the true middle value? So there is a better value in presence of outliers. The better average is median. Okay, so we have to use median when there are outliers in the data. Instead of mean, we can use median. When there are outliers in the data, we have to use median. How do we calculate median? You just arrange the data either ascending or descending order. Now this 9 is still here, and take the middle value. So that way, when you arrange the data ascending or descending order, the middle value comes to be 1.4. Looks like, yeah, that is believable. Like you can actually find it out as, that looks like a, you know, true average value. Just give me 1 second. So when there are outliers in the data, the measure that we are going to use is median instead of mean. So that is the difference. Is it clear why we are going for median instead of mean? Median is the true middle value. So since we are arranging the data either in ascending or descending order, even if this value, the outlier value is 90 or 900, it doesn't matter. The middle value will be 1.4 only, right? So that is the true middle value. That is the difference between mean and median. Okay. So when we say average, we can, say it as either, we can consider that as either mean or median depending on whether there are any outliers in the data or not. So let's see a quick demo. Okay. We take this data, income data. Okay. Income data has these fields. Now what is the mean of capital gain? I'm doing this. That is the mean. Now what is the median? 0. What do you understand from this? So I took a variable called capital gain. Now I calculated the mean. I got it as 1077. I calculated the median. I got it as 0. What is the meaning of that? What do you understand from here? Can I say there might be outliers in capital gain? That's why when yeah, there might be outliers in the capital gain. That's why when I calculate the mean seem to be very high. Whereas median is calculated by ordering all of them, the middle value seem to be 0. So that's a good observation. So we need to be careful. When there are no outliers, mean and median will be anyway nearby, right? Like if there are no outliers at all, then mean, whether you are calculating mean or median, they will be nearby. If mean and median are far away, that gives you a small idea on the outliers that you might get. Okay, so if there are outliers present in the data, median is the measure that you should consider. That is the true middle value. If there are no outliers in the data, anyway mean and median will be same, right? So that's how you should decide whether you should take mean or median. Okay. So go ahead, do this exercise, import online retail sales data, okay? Find the mean of unit price, find the median of unit price. Is the mean equal to median? If they are equal, that means there are no outliers. If they are not equal, they are far away from each other, there might be outliers, okay? Then we might have to consider median as the middle value. Do it quickly right now. Online retail sales data. Mean is nearby median. If you are finding that, then there might not be any outliers. Let me quickly do it. So this is the data set. Let me find the mean 4.6. Let me find the median 2.08. Not a big difference, but still, like, we are still not sure, but yeah, doesn't look like a huge difference. In fact, later on we will learn a concept in the same session, outlier detection using box plots and other things. Then we can actually clearly see whether there are any outliers or not. As of now, this gives a slight indication. That's it. Okay. As of now, we can't say anything from here. We can take mean or median directly, any one of them. So from standalone mean and median, we are not able to tell whether there are any outliers or not. So we calculated mean and median directly. Let me see in quantity. Mean is 9.5, median is 3. Oh, looks like there are outliers in the quantity variable. Again, we are not 100% sure. Okay. If there are any outliers or not outliers, we can only tell that by looking at the box plot. Okay, we will discuss about box plot in some time. Everybody done with the exercise? So whatever we have seen till now, these are measures of central tendency. Now there are something called dispersion measures. What are dispersion measures? So let's try to understand this. Okay, there are two company stocks. Okay, company A, the stock value is 43, 44, 0, 25. 20, 35, okay, or it's not stock, maybe it's profit. So two companies, they are posting their profits in last 14 quarters, maybe it's in $1 million or thousands of dollars, we don't know. So these are the profits of these two companies. There is company A, company B, okay. Now if we look at company A, there are some losses as well, and there are some places where they made a lot of money. Look at company B, they are kind of really consistent, right? They never made losses. But if you look at their mean, if you actually take down all these values and calculate the mean, you will get 15. So 15 is the average profit for company A, 15 is the average profit for company B. Does that mean company A and company B, they are equally, I mean, they're performing equally, both of them are good companies? If you have to buy the stock of a company, which stock you will buy, company A or company B? Which stock, I mean, which company is less risky? Tell me. Company B is less risky because they never made any losses. They are making steady profit every quarter on quarter. Now, what is that we have observed? It's not just the average that makes sense all the time. We might have to look at the deviation from the average or the dispersion or the overall spread, right? So it's not just the average value. If you take two variables, their averages are same, they may not be actually same all the time. It's the deviation that matters sometimes, okay? So how do we find the deviation, okay? So there is a measure called standard deviation, or it is derived from variance actually. So how do we quantify the deviation? How do we quantify the deviation? Here is how we, to quantify the deviation, we have to use a metric called standard deviation. So we have to find the standard deviation or variance. I'll try to explain you the formula, the way it is derived, okay? How do we derive variance? Try to understand it. Then you will appreciate why variance is a good measure of finding the dispersion or the deviation in a data. So these are the values of the company A profit values, 43, 44. You have seen that, right? 43, 44, 0, and all that, 21. These are the values, okay? What we want to measure, we want to measure the deviation, okay? We want to measure the overall deviation in company A. What I'll do is, I'll find the median, a mean, that is 15. Then I found the value minus mean, 43 minus 15, 28, 44 minus 15, that is 29, 0 minus 15, minus 15, 25 minus 15, 10. So like that I found the deviation. Similarly, these are the values of company B. Company B values, and their average is 15. I found the value minus mean. You can already observe the deviations are less for this company, the deviations are more for this company. But if we just take the sum of deviations, since some deviations are minus, some deviations are plus, all the time this sum of deviation comes as 0. Here also sum of deviation will be 0. Here also sum of deviations will be 0. So what we want to do is, we take the deviation, take the square of the deviation. Deviation, deviation square. Minus 15 is the deviation, square is 225. Now we will take the sum of all such square deviation. Average of all the square deviation is 352. Average of all the squared deviation is 4.9. So average of all squared deviation is nothing but variance. Variance of company A is 352. Variance of company B is 4.9. These two values can be directly compared. So variance of company A is higher. Variance of company B is lesser. Square root of this variance is nothing but standard deviation. So this is how variance is calculated. Xi, the original value, minus x bar, the average value. We took the deviations, that is not sufficient. We took the square of that. Average is nothing but all those squares divided by count. So that is how we calculated the variance. Higher the variance, more the dispersion in the data. Lower the variance, less the dispersion. Most of the data is concentrated around the mean value. High variance, lot of data is sparsing, I mean here and there. We have seen already the application, so the consistency if we are looking for, then we might go with variance wherever there is lesser. Since we have squared that up, it's a good idea to take the square root of it as the standard measure. So the variance is this is called variance. The square root of that, simply the square root of the value that we have calculated, square root of the variance is called standard deviation. Clear? So standard deviation of first one is square root of 352, standard deviation second one is square root of 4.9. Square root of variance is called standard deviation. Is the concept clear? The concept of variance and standard deviation as a measure of dispersion in the data. Are we getting the real sense of dispersion in the data? Yes? Yeah. Cool. So let's do one simple example. Okay. Then we will do one exercise. Okay. So what I'll try to do is I have the income data. In that there are several countries. Okay. So within this income data, there are several countries. Cambodia is there, Canada is there, England is there, etc. So this is USA census data. What I want to see is within USA and outside USA, is there any income deviation difference? Okay, I'm preparing USA data and other data. Okay, so let me prepare USA data. Wherever native country is USA, I'm taking that data set and storing it in USA income. What is the size of this data? 29,000. Other income. Okay, what is the size of that? There are 3,000 such observations are there. So within USA and outside USA. So now within USA, I want to find the variation of education number. There is a variable called education number within an income data set. So USA income has a variable called education number. We can see that names of USA income, it has education number. Okay, within USA, what is the education number? Variance and standard deviation. Variance is 5.7, standard deviation is 2.3. Okay, that is within USA. Now other countries, what is the variance? 13. Okay, other countries, people who are coming from other countries, their education is differing from a lot, their standard deviation is higher. So people who are in USA, I think consistently stopping at one point, like maybe all of them are doing one particular education, whereas people from other countries, some people are coming for normal daily jobs, some people are coming for high paid jobs. So education is varying a lot. That is what I'm trying to prove here. Is this clear? The way we calculate variance is you just give the dataset name, dollar variable name, var is the function for finding variance, SD is the function for finding the standard deviation. Is it clear? Yes. Let's do an exercise. I'll explain what is it here. On online retail sales data, tell me the variance and standard deviation of unit price. Similarly, same data set, tell me the variance and standard deviation of quantity. Tell me which of these two variables are consistent. Not that we want to compare them, just we'll calculate variance and standard deviation, find out whether unit price is consistent or quantity is consistent. Let's move on. Percentiles and quartiles. You might have heard this term so many times. So and so percentile, so and so quartile. Okay. What exactly is a percentile? Okay. Let's try to understand that. A student attended an exam, okay, with 1,000 other students. Okay. There are 1,000 people, 1,000 students who attended an exam. He got 68% marks. His marks are 68%. That's what his score is. Now tell me whether he is a good student or bad student. Make a guess. A student attended an exam with 1,000 other guys. He got 68% marks finally. He's a good student or bad student? Now it's all relative. What if the overall, yeah, it's difficult to predict. What if the highest marks itself is 69%? That means this guy is really good, right? What if the highest marks is 100% and the least is just 66% and he got 68%? That means this guy is not really good. He is in the lower percentiles. If he is near to the highest marks, then he is at the highest percentiles. So just by looking at the marks standalone, one student, it might be difficult to predict whether he is a good student or bad student. That's why instead of looking at the marks, let's look at his percentile. Okay, he got 68 marks. Okay, with 68 marks, he stood at 90th position, 90. So there are 910 students who got less than 68, 89 students who got more than him. What do you say? He's a good student or he's a bad student? There are 910 students who got less than 68. There are 910 students who got less than 68. Only 89 got better marks than him. Yeah, he's a good student, right? He is at the top percentile. So only 10% got better than him, 90% got less than him. So he is standing at 90th percentile. Why did I say 90th percentile? Because above him there are 10%, below him there are 90%. This guy falls in 90th percentile. So instead of just 68 marks, 91st percentile gives a good idea on his performance. That's why most of the times in the exams, they mention the percentiles rather than the marks, because just by looking at one person marks, we won't be able to tell whether he performed good or bad. Is that clear, the intuition behind using percentiles? Yes, yeah. So percentiles make the data easy to read sometimes when we are comparing with the rest of the population. So what is the pth percentile? P% of the objects or observations are below it, 100 minus P% are above it. Let's say if somebody is 90 percentile, 90% is below it, only 10% is above it. Marks are 40, but percentile is 80. What does that mean? So 80% of the cat percentile means 20% are above him, 80% are below him. So percentile even help us to get a good idea on the outliers. I'll explain how it is done. Okay. For example, the highest income value is 400,000, that is 4 lakhs. But 95th percentile is 20,000 only. It's a perfect example in India. The highest income value is running into millions. But the average income, or even if you take 95th percentile, is 20,000 only. Only 5% of the people have more than 20,000. Rest of the 90% having less than 20,000. But what is the highest value? It is running into crores or something like that. So that means 95% of the values are less than 20,000. Try to understand what I'm saying here. 95th percentile is 20,000, which means 95% of the values are less than 20,000. So the values near 400,000 are very clearly outliers. Some values are very much different from rest of the whole data set because 95% of them are less than 20,000. Remain within remaining 5% there is a value that is as high as this. Now that is a clear indication of outlier. So percentiles give us a good idea on outliers. So the percentile divide the whole population into 100 groups, whereas quartiles divided into 4 groups. Okay. I mean, just from percentiles, sometimes we talk about quartiles. So 25th percentile is first quartile, second quartile is 50th percentile, third quartile is 75th percentile. Now, why am I talking about quartiles? You will get to know shortly. Percentiles concept, have you understood clearly? Yes, yeah, okay. Now, what is a quartile? If this 25th percentile is called lower quartile or first quartile. 50th percentile, that means 50% of the observations are above that value, 50% are below. That is called second quartile or median. Median also calculated like that only, right? We arranged everything in an order. The middle value is median. Middle value is nothing but 50th percentile, which is nothing but second quartile. Third quartile is 75th percentile. That means 25% is above, 75% is below that particular value. Now here comes the real big use of percentiles and quartiles. We can create something called box plots that will help us in finding out the outliers. But before getting there, we will try to see uh, how to calculate percentiles and quartiles. Given a variable, what are the percentiles and quartiles? We'll try to see that. So let me explain you first of all how to calculate percentiles and quartiles. So this here is this capital gain value. So what is the summary of capital gain? So minimum is 0, first quartile 0, median 0, mean is 1078, third quartile is 0, maximum is 100,000. So we anyway doubted capital gain has some outliers or something. So how do we calculate quartiles? We have to write quantile is a function, quantile. Then we can give the percentiles that we want to take. 0 means the minimum value, 10th percentile, 20th percentile, 30th percentile, 40, 50, 60. I wanted all the 10 distinct percentiles. So from the capital gain, 0, everything is 0 except after 90% there are some values. If you remember this capital gain that we had earlier, that has some outliers, right? That's what we thought, mean of capital gain. Mean we got it as 10,000, median. How much median we got? Obviously 0, right? Median 0. Why this happened? Because 10 percentile, 10th percentile is 0, 20th percentile is 0, 30th percentile is 0, 90% of the values are 0 only. Only 10% of the values they run into almost 99999. That is just because of these values we got the mean as 1000. Just because of this last 10%. I'm not even sure they are last 10%. We can even go further. We can even write 0.95. So that will give 95th percentile also. Okay, looks like yeah, after 90 percentile it is going beyond that. So last 10 percentile has some real high positive values, because of that mean is high. Similarly, we can see capital loss, how it is distributed. Similarly, capital loss is also like that. That's how we can calculate the percentiles. Let us see number of hours per week. This is working hours per week. How people are, how much time people are spending. Let's say everybody is spending 40 hours or some people are spending more than 40 hours. What percent of the people are spending how much time? Now I'll take some time to explain what exactly this whole percentiles and how to interpret them. Please concentrate here in this particular uh, concept. So number of hours per week, this is working hours. Okay, so 10% 24, what does that mean? 10% of the people are working 24 hours or less. That's it. 10% of the people are working 24 hours or less. 90% of the people are working more than 24 hours per week. That's what the US Census data says. 90% of the people are working more than 24 hours per week. 20th percentile is 35. That means only 20% of the people are working less than 35 hours. Remaining 80% are working more than 35 hours. Am I making sense? 50th percentile is 40. Half the people are working less than 40 hours. Half the people are working more than 40 hours. Almost half the people are working more than 40 hours in a week. This is US Census 10 years back, mind you. I think they might have worsened. I don't know. What is worse, I don't know. 80th percentile is 48. That means 80% of the people are working less than or equal to 48 hours. 20% of the people, there are 20% of the people in a week, they are working more than 48 hours. Oh my God, there are people working 99 hours per week. Maybe an outlier. We can't really believe this thing. Maybe some research scholars. We don't know. What does this say? 90 percentile? 90% of the people are working less than 55 hours. There are 10% of the people who are working more than 55 hours. Try to understand this. The way we say it is 90% of the people are working less than 55 hours. There are just a 10% of the people who work more than 55 hours. They work up to almost like 99 hours per week. Is this clear? The concept of percentiles, the way we should read it. Clear? Cool. So let's do an exercise then. There is this bank telemarketing data. There is this variable called balance. Okay. What is balance? This, it's account balance, I think. So are there any outliers in account balance? Let's see the percentile distribution. How much, what percent of the people have lower bank account, lower balance? What percent of the people have high balance in their account and all that? So let's do this exercise. Bank telemarketing data. Before you start this, we'll take a short break here for 5 minutes. When we come back, we'll start with bank telemarketing. Okay, cool. Yes, we are back. Anyone finish this exercise? Bank telemarketing data is here. Here is the balance. Minimum, maximum, quartiles, mean, median is given in the summary. To get the detailed summary, we'll take first quartile, 10th, 0 minimum value, 10th percentile, 20th percentile, 30th, 40th, etc. Then we will see whether there are any true outliers. Let's try to analyze this. Outlier. This is the distribution of the variable. Minimum is minus 8019. Some negative balance, maybe loan or something, who knows. 50% of them above 448, 50% below 448. And the maximum running up to almost 102,317. Now tell me, what percent do you think are outliers? Looks like there are outliers, that is clear from this. What percent of the data has outliers? From here, can you tell me what percent of the data has outliers? I would say maybe 60 to 70% is outliers. No, I would say till here it's fine, like 60% are less than 701, 30% are more than 701, right? That is also fine. Now 70%, like 30% are more than 1000, 70% are less than, this is also fine. I would say last 10%, these are outliers. Like 90% of the people have balance less than 3000. 90% of the people have balance like usual balance. They are not outliers. It's okay to have 3000 as balance. But some people have much more balance than, yeah, 90 to 100%. That will be like 10%, right? In overall, you are saying from 90 till 100th percentile looks like outliers. That means that is forming almost a 10% of the population. Even we can further drill it down. Okay, see whether looks like from this graph, it looks like from this data, it looks like even this is fine. Till 95% this looks fine. Anybody ready to agree with me? Till 95% I'm finding it fine. I'm only finding it outliers as last 5%, right? Maybe you can even further drill it down. Even this first 10% also, you can drill it down. This is also outlier, right? Just in the beginning, there are some outliers. In the ending, there are some outliers. Yes, there are some outliers in the data that is clearly visible from percentiles distribution. That is what we did with balance. Are there any outliers in age variable? Here is the summary of age. Minimum is 18, maximum is 95. Let us see the percentiles. There are 50% of the people less than 39, 50% of the people less than more than 39. 60% is 42, more than 42. 90% of the people less than 56, 10% are more than 56. I don't think there are any outliers. People can live up to 95 years, right? Who said one can't live, right? We can't call them outliers. 95%, oops, looks like maybe an outlier. Yeah, there are outliers, but not impossible to get. So I would like to stick to the point that there are now outliers in age, whereas in balance, there are some outliers. Do you agree with me? Are you finding a real good sense of finding out outliers in the data? This is very important when it comes to predictive modeling. If your data has outliers, the whole analysis, the whole final coefficients that you might be getting, the final model will be affected by these few outliers values that are there present in the data. So it's very important to see the variable distribution like this. Is it clear? Now there is a pictorial way of finding out outliers that is called box plots. Box plots are used for outlier detection. Let's try to understand box plots. What are box plots? So box plot has box inside them. That's why they are called box plots. That is not a joke, that is true actually. So a box plot, inside a box plot, a box is formed by these two values. So uh, a box plot contains 5 values. The box plot is formed by 5 values. First value is minimum value. You put the minimum value. You put the first quartile value, median value, third. Fourth one is third quartile, that is 75th percentile. Then the maximum value. If you put all of them in one chart, that is called box plot. Minimum, first quartile is also known as lower quartile, median, third quartile is known as upper quartile, then the maximum value. If there are any outliers in the data, yeah, the summary is giving kind of all these values. If there are any outliers in the data, this box, you see, the upper side of the box by here, by third quartile, 75% of the population is covered, right? If there are any outliers, 75% of the population will be kind of very small, then the maximum value will be far away from the box. If the box plot is not looking like a box, it's just looking like a line, then you can clearly identify the outliers. I'll show you an example when there are outliers, when there are no outliers in the data. So a box plot is used for identifying the outliers. It is formed by taking 5 major summary values. Yeah, it is a summary. Minimum, first quartile, median, third quartile, and maximum. Okay. So if this is the box plot, okay, a variable minimum value is 5. First quartile value is 10. What does that mean? 25% of the values are less than 10. 75% of the values are more than 10. Possible? Median is somewhere between. Now the third quartile is 15. That means 75% of the values are less than 15. Only 25% of the values are more than 15. Understand this. 75% of the values are less than 15. Only 25% are more than 15. Now within that 25% remaining values, the value is going as high as 120. So you are saying on one side my whole population, 75% of the population is less than 15. On the other side you are saying I can attain a value as max as 120. Isn't that a clear indication of outlier? Some values that are really different from rest of the whole population, or at least 75% of the population is squeezed within certain limits. Rest of the values are going here and there. So when you can't see a real box in your box plot, that means if you can see this, okay, the example that you can see here on the right hand side, you just see a line, right? In fact, that's a box that is containing 75% of the values. Remaining all these dots, they are just 25%. Since their outliers are so much impacting, that's why you're not able to see the box. That box represents 75% of the values. So you can clearly say there are outliers in this data. Is it clear? Yep. Only box plot used to find the outliers. Box plot is one of the ways, or one of the most widely used ways of finding the outliers, or the easiest way. You can use some other distributions and all that to find out whether there are any outliers or not. Yeah, but box plot is the easiest and the right way of finding the outliers. Okay. Now let us try to see whether there are any outliers in capital gain. I'm trying to draw the box plot. Can you see the box plot? So what does this mean? What does this line say? Remember, this is not a line. This is not a horizontal line. That is a box. That is a box. I mean, no box means that box is squeezed in that. Okay. So this box represents 75% of the population. Can I say box represent the upper limit of the box? Till the upper limit of the box, 75% of the population is covered, right? Remaining is only 25%. So definitely there are outliers. That's why box is squeezed. If there were no outliers, maybe it might have looked like this. So this is the one that has outliers. If you see the percentile distribution, you can clearly see that from 93 onwards, there are some values. Till that point, there are all zeros. So these values, the 7% are clearly different than the rest of the 93% of the population. These are outliers. They are clearly visible from the box plot even without looking at the percentiles. I can say that. Now education number looks like there are no major outliers. The same can be proved by looking at the percentiles distribution. 50% are less than 10, 50% are more than 10, maximum value is 16. Can you find any outliers? Can you say the whole population, like there are no major outliers in this data, all of them are nearby, there are no values that are totally different from rest of the values in this data? Can you say that? Can I confidently say education number has no outliers in this data? Education number has, a kind of well spread data. You can also see that from the box. So whenever you see your box is squeezed, whenever you feel like there is no box, that means only horizontal line is visible. That means there are outliers that are actually pushing. So that one horizontal line that you see is 75% of the population. Is that clear? Can we do an exercise? Let's go. Again, bank telemarketing data. We already suspected outliers. Go ahead, draw the box plot, prove your point. Yes, there are outliers, Your Honor. And then let's come back to one more variable, age. So draw the box plot for balance. Draw the box plot for age. Let me draw the box plots for balance. Box plot for balance. Very clear from that there are not only for this variable balance, there are not only high side outliers, looks like there are low side outliers as well. Do you understand these two terms? High side outliers, low side outliers. That means there are some values that are like really high as well as there are some values that are really low. So there are high side outliers, low side outliers. The box squeezed in between here that represents 75% of the population. Remaining are the outliers that we can see. Same thing can be seen from summary. There are some high side, there are some low side outliers. Same thing can be seen from quantiles, percentiles. There are some values that are high negative values from 93% onwards or 96 on. I think last 2% is the one that is troublesome, or even, yeah, 98% is also fine. Till 98% I am fine. Last 2% of the values, last 2% of the people, they have huge amount of balance in their bank accounts. Okay, now let's come back to the variable age box plot. So see here, R is kind of behaving over friendly with us. It is identifying outliers for us which we don't want. Okay, so basically we will analyze by ourselves and find out, so why these points are highlighted compared to others. R is doubting them as outliers and giving us like as a suggestion that we can consider them anybody above 70, I think, as outlier. But I think, yeah, 70 people can live after that, right? So here is a summary. Third quartile is 48, maximum is 95. Let's see the percentiles. Again, I think we already discussed this. 50% below 39, 50% above 39, 90% below 56, remaining above 56, 10%. Beyond this, if you want to even further go, I'll take 93rd percentile. There is no rule that you should take only 93rd, 95th, nothing like that. I'm just taking it in my way. 0.97, comma 1. So 93rd percentile is 58, 95th percentile is 59, 97th is 60. Yeah, last 3% of the people may be called as outliers. Maybe. Because 97% of the people are dying by the age of 60. Why these rest of the 3% are living till 95? Yeah. But anyway, so maybe 3% outliers are there, but compared to balance that has so many outliers, whereas age has lesser percent of outliers. Am I making sense? Yes. Cool. So can I go to the next topic? Yes, we're doing really good today. So creating graphs in R. How do we create graphs? Again, there is nothing really teach in creating graphs. Basically, we just need to take the data, use the right graph method, right graph function, and then take the input, give the right input data and create the graph. Okay, how do we do it? Okay, here is how we create the scatter plots. Data, so I have the data. This is the usual data sets that we have inside our. I'll take cars data. Here is the cars data, and then we'll try to plot car speed versus distance. So I have the cars data which has two variables, speed and distance. I'll just use plot command, plot car speed versus distance. So speed is on the x-axis, stopping distance is on the y-axis. As usual, if the speed is high, stopping distance will be more. If you are traveling at 25 miles per hour, then your stopping distance will be higher. I think 120 inches or something, or yeah. So that is simply drawing the scatter plot. Very quickly you draw the scatter plot by downloading sporting goods sales data. Draw a scatter plot between average income and sales. Quickly import sporting goods sales data. So we're trying to draw the scatter plot. So here is the sporting goods sales data that I'm trying to import, and then it has average family size, average income, male female gender ratio in a city, and the sporting goods sales. So company like Decathlon or some other sports company, they have set up some shops in some cities. They have the data on average income of the city, male female gender ratio. Maybe some of these affect the sales. We don't know. Unemployment rate, under 35 population, number of schools. Maybe all of these are variables that will affect the sales. Can we study their relation? Yes, we can. So we can plot average income versus sales. Average income and sales has nothing to do. Looks like there is no pattern. As average income increases, sales might increase or decrease. That's what I can infer from this graph, that average income has nothing to do with the sales. Do you agree with me? Can you see any pattern? What about under 35 population versus sales? As the under 35% population increases, sales increases. Can you conclude that from looking at the graph? Yes, right. So that is the use of scatter plot. As average income increases, the sales is neither increasing nor decreasing. They are independent. Whereas population percentage, under 35 population, wherever under 35 is more, 80% of the people are youth in a particular city, then the sports, sales is higher. So it's those, I mean, those cities, in those cities, the sales is higher. Maybe it's time to set up shop there. Okay, if you are a sporting goods company. So that's how like we can interpret the scatter plot. Clear? Shall we move on? Okay. Now there is something called bar chart. Again, this is a different type of chart specifically used for frequencies and counts. Okay. So here is an example. You have a data set called empty cars data. Empty cars data has What variables? Let me see. It has car, mpg, number of cylinders, days, HP, all the car related variables. What we are concerned about is how many cars are there with cylinders. So we want to see count of cars with number of cylinders. Simply I'm creating a table. So for that I'm drawing a bar plot. So there are some cars with 4 cylinders, some cars with 6 cylinders, some cars with 8 cylinders. The cars with 8 cylinders are the maximum. So if you have a discrete or a categorical variable that is cylinders, so number of cylinders are 4, 6, 8. Out of that, so first we created a table, okay, then only we can draw the bar plot. So I created a table for this variable. This works only for a non-continuous or categorical or discrete variables, this bar chart. Okay, basically we want to see for each category what is the count. That's it. Similarly, number of gears. Okay, some cars have higher gears, some cars have lower gears, right? So first we will create a table. So how many gears are there total? 3 gears are there, some cars, 4 gears are there, 5 gears are there for some cars, right? Then how many cars are there with 3 gears? 15, 12, 5 gear cars are less in this particular data set. Maybe very old data when 3 gear cars were very famous. Okay. Am I audible now? Hello? Yes. Uh, from what point I have to repeat? Did you lose me during cylinders? Scatterplot, everybody heard correctly? Scatterplot, huh? Yes, okay. So let me repeat the bar chart. Bar chart works only, I mean, bar chart is used when you have data, something like that. Let's say this whole data set has so many cars, okay? Some cars have 3 gears, 4 gears, 5 gears. So first we have to, then I want to draw a bar chart where how many cars have 3 gears, 4 gears, 5 gears, so that just by looking at the chart, I can quickly tell, okay? For that, first we need to take the data and create a table out of it. Now, how does this table look like? This. So there are some cars with 3 gears, 4 gears, 5 gears. There are 15 cars with 3 gears, 12 cars with 4 gears, 5 cars with 5 gears. Then bar plot. So I just need to say bar table gear. So this is the table that we have created. Then create a bar chart out of that. So I'm creating a bar chart out of that. I gave a lot of other options like color, etc. Right? So finally, it created a bar chart. 3 appears to be bigger bar because there are many cars with 3 gears. Okay, is that clear? Okay, do this exercise on the sports data set. Do this exercise on family size. How many families, like in this whole data set, how many family, what is the family size? Family size chart we want to see, a bar chart. Family size might be 2, 3, 4, 5, 6. Okay, how many? What is the highest family size? We can get a feel of that by looking at the bar chart. Sports data. First I'm creating the family table. Let me print the family table. Family size is 1. What the hell? Family size is 1, 2, 3, 4. Bar plot. So family size whenever it is 2 or 3, they are higher, 4 is lesser. You can ask me, can I put labels on it? Yes, we can. Can I change the color? Yes, we can. Can we format it? Yes, there are so many things that we can do. This is a simple plain bar chart that we used as it is. That's it. Then the last chart for today is trend chart. When you are dealing with time series, trend chart is a good way of showing the pattern or the sales or the number of customers over time. Air passengers data, we know these are the air passengers between 1949 to 1960. From January 1949, 1960, December, there were very few passengers around the world. So what is their pattern? So this is how you just need to write plot. Obviously in 1950 there were lesser people. As we go on till 1960 and all that, there were more people. One thing is very clear, there is still seasonality. Like there was a particular season, there were very less number of passengers. There was a particular season, there are very high number of passengers. Looks like that is Christmas time. That's where we use time series analysis to forecast the future values as well. Yes. Let's go and do one more data. Trend chart on Johnson & Johnson data. Draw a trend chart for UK gas data. UK gas data is already inbuilt in R, so you can directly use UK gas. Okay, quarter on quarter UK gas, this thing. So directly you can write plot UK gas. Do it, create. So here is UK gas. Write a plot UK gas. Can everyone hear me? Okay. So you just need to write plot UK gas. This is how UK gas consumption looks like. Over a period of time, we see both volume increased, even the seasonality. Plot Johnson & Johnson, maybe Johnson & Johnson stock price or sales, I think. If you want to know what exactly is this data set, we can simply say question mark Johnson & Johnson. It will tell earnings per Johnson & Johnson share. Wow, they did really well according to graph, right? Yes. There are some more ways of customizing these graphs. The graphs that we have seen now are very basic graphs, and R is known for its graphics abilities. Okay, there are very good packages, dedicated packages. Some people have dedicated their lives to just create some beautiful visualizations on R. One of such packages is ggplot. I'll just show it to you, will not do an exercise. So ggplot2 is the library. Using ggplot, using qplot, we can draw some beautiful graphs. Okay, the same scatter plot that was looking really scattered wavered, last time, that looks beautiful here. If we have qplot, when we are documenting, it's better to use these kind of graphics. It's the same thing, nothing different, but it looks beautiful with all the colors and the type of shapes that we can use. Okay, there are so many such packages in R. When you are actually working with the real data, instead of showing basic graphs which are inbuilt in R, it's better to use some of the packages like ggplot and other packages. Okay, we just need to use some of the inbuilt parameters and objects to make the graphs beautiful. Is that clear? I leave it to you as an exercise. You can try this out, ggplot. So that is it. What we discussed here, some of the basic statistics, what is mean, what is median, what is variance, how do we find outliers, that is very important topic. How do we uh, how do we analyze the distribution of a variable? How do we find what percent of the variables are, I mean, what percent of the values in a particular variable are outlier? Okay. And then we saw how to draw the graphs, etc. inside R. So that finishes our R programming introduction for a data scientist. This is just a programming introduction. Before we start analytics, this much of R one should know. If any of these concepts, if you haven't understood, I mean, if you're still having any doubt or if you are not clear, I'm going to upload this video anyway. Please go through it once again. Even then, if it is not clear, then you can message me. I will uh, try to spend some additional time with you to explain you that particular concept. As of now, are there any questions for me?